For our last video in this section, we're going to look at some special cases of systems of equations. This first graph should look familiar to you because this is all of the examples that you've seen so far. They have looked like this. These kinds of lines are called intersecting. They have one solution because remember that the solution is the point where the lines meet. And in this picture, the lines meet at one point. Now, sometimes you'll hear the name for this type of a system called consistent and independent. Consistent means that there is at least one solution to a problem, and independent means that there is only one solution to a problem. This second picture has a set of parallel lines. So the type of lines for that picture is parallel. And if the solution to a system is the point where the two lines meet, and part of the definition of parallel lines is that they're lines that do not intersect, that means that there is no solution to a system of equations that happen to be parallel lines. And the name that we use for this, the vocabulary word for this, is we call this inconsistent. Again, remember that consistent meant that there was at least one solution. Inconsistent means that there is no solution. And this last one doesn't really look like a system at first. What's going on here is that first you graph your first line, it looks like this, and then you go to graph your second line and something kind of unusual happens in that it's the exact same line. So if you're looking for where they intersect everywhere. So the type of line is that it's the same line, and because they intersect everywhere along the line at very many places, we say that there are an infinite number of solutions Earlier in the year, you might recall that we said that sometimes the solution was all real numbers. This is not all real numbers because even though there's an infinite number of solutions along this line, like here's a point, here's a point, here's a point, all of these are points along that line, there's also points like over here or over here that are not solutions. So not every point is a solution, but there are still an infinite number of solutions. And lastly, the name we give to this type of setup, we call this consistent dependent. Remember that consistent means that there's at least one solution. Dependent means that there's more than one solution. So let's look at an example. Here we have the equations y equals 3/2 x minus 3 and y equals 3/2 x minus 1. Now, before we even do this problem, you should know how it's going to turn out because you know something about slopes. They both have the same slope and they both have different y-intercepts. So that first graph, if I compare that to y equals mx plus b, the y-intercept is -3, so I'm going to start my graph over at 0, -3. And then the slope is 3/2, so to get my next point, I'm going to go up 3 over 2, up 3 over 2, and I'm going to continue to do that until I run out of room on my graph. And then I'm going to go in the opposite direction. Instead of up 3, right 2, I'm going to go down 3, left 2. All right, and then there is my graph for the first line. For my second line, the slope is 3/2 again. The y-intercept this time is -1. So I'm going to start at the y-intercept at the point 0, -1, and I'm going to go up 3 over 2, up 3 over 2, and continue to do that until I kind of run out of room there. And I can go the other direction. I can go down 3, left 2, down 3, left 2. And I can connect those orange points. All right, and hopefully you knew this before you saw it, because those lines had the same slopes and different y-intercepts. That means they're parallel and there is no solution because the lines never cross. Now, if I changed this problem just a little bit and I changed it to y equals 3/2 x minus 3 and y equals 3/2 x minus 3, well, that's the same line. I'd end up with just this red line on my graph, and when I go to graph the orange one, it would be right on top of it, and then I would say that there are infinitely many solutions.